Good afternoon, students. I am Chaitanya, Assistant Professor in Mathematics, Freshman Engineering Department, Institute of Aeronautical Engineering. And in the last lecture, we have discussed the Carl Pearson's measure of correlation, which is an important measure to measure the relationship between two given variables x and y. And today's lecture, we are going to discuss one more important mathematical measure of correlation, nothing but Spearman's rank correlation. So let us see the contents of the lecture. So today we are going to discuss the Spearman's rank correlation and its properties and a problem solved by Spearman's procedure of calculating the rank correlation. As I said earlier, Spearman's rank correlation is nothing but one alternative measure of correlation for Carl Pearson's quotient of correlation. Actually, Carl Pearson's quotient of correlation has two major drawbacks. Number one, it involves so many calculations. That means it involves laborious calculations and tedious tasks of mathematical computations. So to overcome these drawbacks, Spearman has introduced the rank correlation procedure. In this method, in the place of original values, we'll use the ranks assigned to those values. That means every value will be assigned with a rank, and rank is a positive integer. So the calculations become simplified, and hence we'll feel very comfortable with rank correlation, Spearman's rank correlation when compared to Carl Pearson's quotient of correlation. Now let us look into the details one by one. So Spearman's correlation is designed to measure the relationship between two variables x and y where the values of x and y are ordinally arranged. That means, there are two kinds of arrangement of numbers, cardinal and ordinal. Cardinal arrangement means we'll just arrange the values according to their magnitude. That is 1, 2, 3, 4, 5. These are cardinal arrangements. If we give order, then it becomes ordinal arrangement. That means if we say that first, second, third, fourth, fifth, then it is called ordinal arrangement. That means cardinal means 1, 2, 3, 4, 5, 6, and ordinal means first, second, third, fourth, fifth, and sixth, like this. That means we'll be able to arrange the things in a preferential order. That is, which should come first and which should come the next and which should come the next, like that. Then it is called an ordinal arrangement. So let us fix that we have a bivariate data x and y where the values are ordinally arrangeable. Then we can apply Spearman's correlation to decide whether x and y are related to each other or not. So as I said, the data should be bivariate and the measurement, the scale should be ordinal. These are the two conditions to apply Spearman's correlation. Also here x and y should be independent of each other. That means the values of x should be independent and the values of y should be independent of one another. Now, according to the procedure of Spearman's quotient of correlation, first we have to convert the given values into ranks. That means we have to assign ranks to the given values basing on either in ascending order or in descending order. Both the ways will work. But for assigning ranks, we have to follow three conditions posed by Spearman. The condition number one is the last rank should be the number capital N, which is nothing but the number of observations. That is, if capital N is total number of observations, then the last rank of x value should be capital N, as well as the last rank of y value should also be capital N. That means both ranks of x and ranks of y should end with capital N. And second thing, equal marks should be given equal ranks. That means if there is a tie in the values of x, we should assign equal ranks for those values, as well as if there is a tie in y values, we should assign equal ranks to the y values. And the third condition is, once you assign a rank more than once, the immediate next integer rank should be ignored completely. That means If you assign a rank 8 to more than one value, then you should not use the rank 9 for any value. You should completely ignore it. That means we have to ignore the rank which is immediate to the repeated rank. So by using these three conditions, we can apply Spearman's rank correlation to the given data, and we can acquire the values of deviations, and hence we can calculate the squares of deviations, and finally we'll be able to calculate the Spearman's correlation of rank. Let us see the formula and the details in the next slide. So the formula of Spearman runs like this. It is denoted by the Greek alphabet rho, and the formula is nothing but the difference of 1 and a ratio, and the ratio is nothing but the numerator 6 times sigma d square and the denominator n times n square minus 1, where n represents the total number of observations and di represents the deviation between the rank of ith value of x and the rank of ith value of y. That is, if Ri is the absolute difference of xi minus yi, then di is nothing but mod of xi minus yi, and di nothing but mod of rxi minus ryi, and di square represents the square of the difference. So let us see the things more clearly in the next slide. So here, before going to a problem, we'll discuss the properties of the Spearman's correlation quotient, that is rho. As Karl Pearson's quotient of correlation ranges between -1 and +1, the Spearman's quotient of correlation rho will also ranges between -1 and +1. The question is why? Because Spearman's quotient of correlation is nothing but a simple deduction of Karl Pearson's quotient of correlation by using the formula that sum of n integers is n into n plus 1 by 2, and sum of squares of n integers n into n plus 1 into n plus 1 by 6, and ranks are always positive integers, and they should follow these two formulas, that is sum of first n integers and sum of squares of first n integers. We can easily verify that the Spearman's quotient of correlation is nothing but a deduction of Karl Pearson's quotient of correlation. Since Karl Pearson's quotient of correlation always ranges between -1 and +1, automatically the Spearman's quotient of correlation also ranges between -1 and +1. If the value of rho is positive, then we'll fix that the x and y are positively correlated. If the value of rho is a negative, that is ranges between -1 and 0, then we'll fix that the x and y are negatively correlated. Now let us take an example and look into the procedure of Spearman's calculation of correlation in detail. Here we are given with two sets of data, that is the test ranks of 9 teams and one ODI ranks of the same 9 teams. That means we are given with a table which involves two columns, namely the test rankings of 9 teams and the ODI rankings, one-day rankings of 9 teams. The teams are order is as follows: Australia, India, South Africa, Sri Lanka, England, Pakistan, New Zealand, West Indies, and Bangladesh. And the test rank of Australia is 1, and the Australia's ODI rank is also 1. And India's test rank is 2, but the ODI rank is 3. And South Africa's test rank is 3 and ODI rank is 2. Like this, the given table runs as given in the slide. Now we are asked to find there is any relationship between the test ranking and ODI ranking. That means we are going to judge whether the performance of teams in tests and the performance of the teams in ODIs are related to each other. If they are related, are they positively related or negatively related? That means if a team performing well in tests is also performing well in ODIs, and a team performing well in ODIs is also performing well in tests, that is what we are going to decide by measuring the correlation. Let us look into the solution in the next slide. Here we have taken the ranks and we have calculated the deviations in the form of d. That means 1 minus 1 is taken as 0, and 2 minus 3 is taken as absolute value of 2 minus 3 is taken as 1, 3 minus 2 is taken as 1, 4 minus 7 is taken as 3, 5 minus 6 is taken as 1, 6 minus 4 is taken as 2, 7 minus 5 is taken as 2, and 8 minus 8 is 0, 9 minus 9 is 0. And in the last column we have calculated the squares of deviations, that is 0 square, 1 square, 1 square, 3 square, 1 square, 2 square, like that. And we have added all these squares and we obtained the summation di square as 20. Now, according to the formula, the Spearman's formula, 1 minus 6 times summation di square over n into n square minus 1, we have calculated that the rho for this data is 0.833. That means 83% of degree of relationship between x and y. That means x and y are positively correlated. That is, test performance and ODI performance are always positively correlated. And the degree of extent of relationship is 83%. In this way, we can conclude the data. And next problem, we'll look at how we are going to assign ranks to the given marks and how we are going to obtain the Spearman's correlation. Here, the question runs like this. A composite rating is given by executives to each college graduate joining a plastic manufacturing firm. The executive ratings represent the future potential of the college graduate. The graduates then enter an implant training program and are given another composite rating. The executive ratings and the implant ratings are as follows. That means this question says that the members who are undergoing training for an employment, their performance will be evaluated before training as well as after training. And we are going to check whether there is any relationship between the prior to the training as well as the post-training data. That means whether the performances of the employees before undergoing the training and after undergoing the training are related to each other or not. In the exam conducted for 100 marks for the 11 students before they undergone the training are recorded in the first column, and the marks obtained by the same 11 students after undergoing the training is recorded in the second column. That means first column gives you the marks of 11 students before the training, and the second column gives you the marks of 11 students after the training. And the first student got 85 marks in the first exam and 85 marks in the second exam. That is, there is no difference in that student's performance before and after training. But if you see the third student, he got 90 marks before the training and he got only 80 marks after the training. But if you take the fifth student, he got 57 marks before training but has improved his performance drastically, and after training he got 70 marks. In that way the data runs. Now let us check whether the performances before training and after training are related to each other or not mathematically. So first we have assigned ranks to the marks obtained by the students in the exam 1, that is before training. And also we have assigned ranks to the marks of the students obtained in the exam conducted after the training. That is, first column represents the ranks before training and the second column represents the ranks after training. Now we have calculated the deviations between the ranks, and the deviations are like this. That means 1 minus 2 with absolute value 1, 2 minus 1, 3 minus 3, mod of 4 minus 5, mod of 5 minus 4, mod of 6 minus 7. Like that we have recorded all the deviations. And we have calculated that we can calculate the deviations squares, and we can add all the deviations and we can obtain summation d square. And if you substitute the things in this formula, that is the Spearman's correlation, 1 minus 6 times summation d square by n into n square minus 1, we can obtain the value of correlation, and we can verify whether x and y are related to each other. If they are related, whether the relation is positive or negative. So I'd like to conclude the lecture and we'll continue the lecture in the next session with the concept of regression and ranking of tied data, etc. Thank you all.
Like, share, and subscribe. Hit the bell icon for more updates.